All right, good afternoon, everyone. Our group, consisting of Lucia Millar, Robert Scott, and myself, Alexis Guerra, will be presenting to you our senior design project, the natural gait inducing prosthetic. Currently, when patients receive a transtibial or below-the-knee amputation, they're fitted with a passive prosthetic. While the prosthetic allows them to walk again, it doesn't assist in the walking cycle as does a natural leg with a calf muscle. This produces an asymmetrical gait in the patient, which causes back complications, coronary problems, and early mortality. To alleviate this, they've developed active prosthetics that power the walking cycle with a motor. However, these are prohibitively expensive, an example of which costs them $50,000. This is a major problem as the majority of transtibial amputees live below the poverty line.
The objectives of this project were basically to design an active ankle prosthetic that would adjust the push-off force. Also, in doing so, we would do the mechanical analysis of the system, and part of that would be to look at torque so that it can reach the maximum torque required in our torque curve. Another thing would be to reduce the cost so that it's more accessible to people in need, and to make it modular so that each patient can customize it by changing drive motors and springs.
So whenever dealing with any type of engineering system, standards are something to be considered. For any medical device, the first thing you look at is the FDA. Fortunately for us, since our device is non-invasive under Title 21, we don't have any restrictions from the FDA to manufacture our product. In addition to that, we use the ASTM standards and the AGMA. So here you see the biomechanics of walking, also known as the gait cycle, which we'll refer to it later. It starts off with heel strike and ends with toe off. You can break it down to 3 phases. Controlled plantar flexion, which is from heel strike to mid stance. Dorsiflexion is from heel strike to when your heel comes off the ground, and then controlled plantar flexion is from when your heel comes off the ground to when your toes come off the ground. On the photo here, you can see a red spring and a blue spring. The red spring represents your Achilles tendon, and the blue spring represents your interior muscles on your shaft. So these are different type of actuator designs. The most basic is a series elastic actuator, which is a linear actuator in series with the spring. This reduces the total energy required by the system. So if by putting the series spring, you go further on the same battery. A parallel spring will allow you to reduce the peak power required by the system. What we're doing, we're combining a series elastic spring and a unidirectional parallel spring. A unidirectional parallel spring is like a parallel spring, but we only get the mechanical advantage during certain instances of the gait cycle.
So in order to simulate the results of our design choices on our prosthetic, we'll be implementing a mathematical model. In this case, the HillTech muscle model, which is a set of equations that breaks down the musculoskeletal system of the human body into different components. What this will allow us to do is to calculate the torque of the ankle joint at every point in the gait cycle while you're walking, and with this data we'll be able to plot out a curve that will match with our prosthetic. Shown here is a diagram of how the HillTech muscle model breaks down the musculoskeletal system into different components. The spring is the Achilles tendon, and the contractile element CE is your calf muscle. And shown here are 2 sample equations of how it calculates torque at different phases in the gait cycle, such as dorsiflexion and plantar flexion.
This is the Gait lab at main campus on FIU, where we actually recorded gait data that we would later use to be analyzed. The white outline tape on the walkways has 2 force plates underneath that will record force during walking, and the surrounding cameras will pick up these markers, and then that is the setup of how it would look for getting it for the ankle. This is an actual representation of how it looks while standing, and then how it would look on the computer. This is using the markers applying a skeletal system. And this video shows a real-time representation with the vertical force pointing up of me standing on that force plate. And in a later here, it's actually the entire gait cycle. And yeah.
Shown here is a graph made in Microsoft Excel of the data set of torque collected from that test you just saw in the video. So there's a torque value at every point in the gait cycle, and then this is the graph, the curve that depicts that. So in order to actually generate a torque curve from a prosthetic, dozens of equations need to be computed. In order to automate this process, we developed a simulation model in Microsoft Excel that automates all the computation of these equations. And what this allowed us to do is to be able to analyze more designs for feasibility in a shorter amount of time. And our simulation model uses 24 different design inputs or 24 different things that we can change, and it breaks down the entire gait cycle into 80 different points or 80 different data points that will be calculated for it. We use system design checks that automatically checks the design input into the model for feasibility or anything that would render the design unusable, as well as Excel Solver, which actually computes every possible combination of design inputs and gives us the best output for what we want it to do. And shown here is actually an illustration of our simulation model, the design checks on the left, and the two different curves here on the right, the orange being Lucy's curve from the test, and the blue being our prosthetic. You can see after a certain point, they match so closely with each other that you can't tell them apart.
This is the actual trigonometry used that was implemented in the simulation model used. The lowercase letters, the A is the linear actuator, B would be the moment arm, and then C is the distance from the ankle to the top relevant joint.
And shown here in this figure is the series spring assembly. And it's very important to note here that the moment arm on which the force of the linear actuator acts on is actually variable, so it changes with the contraction and expansion of the series spring, and that affects how we calculate torque at every point in the gait cycle.
So when we're deciding between which type of linear actuator we're going to choose, we're between a lead screw and a ball screw. We went with the ball screw design so that during heel strike the system wouldn't lock up. These are the two equations we use to calculate the force and velocity of the ball nut.
And shown here are several equations that depict the importance of how each spring affects the torque or the resultant torque around the ankle joint at different phases, dorsiflexion, plantar flexion, in the gait cycle. So that has to be accounted for when calculating it. And shown here are we use two different methods to calculate the error between the natural and the simulated torque datasets. And for Microsoft Solver, we use a squared mean error cost to show how different the two different sets are and how far the two different curves are.
So from the simulation model, we found out that we need to have a motor that can produce 152 millinewton meters of torque at 12,000 RPM. We're going to put that into a gearbox that has a 12-to-1 ratio, and our lead on our ball screw is going to be 5 millimeters. We're also going to use a 4,800 milliamp hour battery. So when we're just trying to pick which components we want to get, the first criteria was that the components could satisfy what we need, our specifications. The next was the cost. If it was too expensive, the project would not be worth doing, and then if it weighed too much, it would off-balance the data that we received from the simulation model. Here, you can see our major components. On the top left is our maximum motor. Below it is the gearbox. Here's the ball screw mount. Below is the carbon fiber Veriflex foot. Here's our ball nut, and below is our Arduino Mega, which is our microcontroller.
So in order to analyze how effective our design was at lowering the cost of an active prosthetic to give to people in need, we calculated the cost of every component, including manufacturing, and we came up with a figure of approximately $10,000, which is a success. We consider a success as it's 1/5 of the cost of the only existing active prosthetic on the market currently.
This would be what everything looks assembled in SolidWorks with some of the electrical components. On the left is it without the enclosure, and on the right it has the enclosure. Doing a stress analysis, which is where we loaded the top surface with a compressive load of 130 pound force, we were able to find our material to make the enclosure out of. The best material was aluminum, giving us a safety factor of 2.14 and being the lightest as well. Here we did a fatigue analysis where we applied 1 million cycles to the assembly. The purple shows that there's still some life left after the fatigue, after the cycles, and on the left you can see with that life, it can withstand those 1 million cycles.
So the primary performance variable in any given active prosthetic is the amount of assistance it can provide the patient in the walking cycle. This is what we'll be testing with our design. Unfortunately, the motor that we needed to complete our initial design was going to take 10 weeks to get here from Switzerland. So as a substitute to test, we divided the data set collected from Lucy's walking test by a factor of 5, and we built a testing prototype in order to match that new curve. So in order to test, we turned the prototype upside down, fixed it to a fixed base, and attached weights to the end of the foot. If it could lift the weight up, then it produced a certain amount of torque. We added enough weight in order to produce our target peak torque of Lucy's new data set.
So as Alex was saying, so our proof of concept prototype requires a motor that can produce 60 million meters of torque at 11,000 RPM. And we're going to be using a gearbox of 21:1, and the lead on our lead screw is 6 millimeters. And we're 3D printing the casing. So here on the left, you can see the ankle, which has a series springs built into the ankle behind the hinges. And on the right is our gearbox with our motor and our lead screw. So here's our final assembly of the motor and our linear actuator, our chassis, and our power supply. We use a power supply instead of a battery because we didn't want to waste time charging it. So it produced 12 volts with 10 amps. So this was our final assembly. And then here you can see our testing procedure. So what we would do, we would begin it in heel strike and go all the way up to toe off, and we would increase the weight incrementally. So we started at 7.5 pounds because we had faith our design could do it for sure, and we put in increments of 2.5. And then in the middle, you can see the torque that is required, that the motor has to overcome. And on the right, our results were like the effect that it had on the motor. Since the more torque, it would slow down the RPM. So from 7.5 pounds to 12.5 pounds, there was no hesitation in the motor. At 15 pounds, due to user error, we overextended the linear actuator and bent one of the hinges. And then when we loaded it with 17.5 pounds, the hinge failed. But the motor was still powerful enough, so we have faith that it could have lifted the 20 pounds, but we just didn't have enough time to remanufacture the hinge and the spring systems. This is where the hinge broke, and some of the plastic broke with it. It bent the screw and broke the hinge. And this is another photo.
So the way our project had a social and global impact is that it would return a lot of amputees back to the workforce, which would reduce the government and insurance spending, which would then increase economic productivity. The funds not used now for the amputees can then be reallocated to different preventive medicine projects and overall improve public health. The way this project influenced our lifelong learning is that time management is the most essential part of the project, since hard deadlines are very essential. And then the rule of pi shows that it will take you 3.1 times more than originally estimated. So time is very important. Clear communication amongst your group members will avoid having any misunderstandings, and the design process is probably one of the most important things to complete first, as it is the basis of the project. This is our project timeline that we had set in the beginning. We were able to achieve everything in time. As you can see, we have a working testing prototype.
Through the completion of this project, we saw that we achieved our goals of lowering the cost of a prosthetic for commercialization, as well as our alternative designs for the unidirectional and series spring versus the conventional design of a carbon fiber Kevlar leaf spring is effective and viable for commercialization as well. Our maximum torque was almost reached, and our simulation model was partially validated as well, which means we can use this same model for future design iterations.
So the next step would be to experiment with different types of materials and springs to increase the efficiency of our system and the weight and cost. And then we would also like to meet with computer and software engineers to implement our predictive algorithm, which allow to walk without any outside user.
Another ways we can make this better is to add a regenerative power motor control, which would allow for the battery to be charged during the Gait cycle, and then to have a custom mounting block that is lighter and smaller, and to also look into linear actuators that can achieve our required specifications, and to work with a HillTech muscle model expert.
Before we leave off our presentation, we'd like to thank those who have helped us along the way, including Melissa Morris, who helped us very much with getting everything together, our advisor, Dr. Tosunoglu, Dr. Leonard Elbaum, which provided us the Gait lab, and as well doctoral candidate Andres Pena, which provided us with the problem statement to formulate this project. Thank you very much for attending our presentation. We'll be opening up the floor for questions.
I guess I'll go first. Did you guys look at scalability for different size, different gaits? I mean, you did tremendous work for a single gate, but I was curious as to what you may have looked at for that.
We didn't design for other uses. Our design, or this one in particular, was based off of Initially, it was based off of standard John Doe, which is a 5'10", 160-pound male. However, the good thing about the simulation model and making it in Excel is that, let's say if we had a different torque curve or different max load of the person's weight or different walking speed, we can easily get a quick design for that load, that situation.
The equations that you showed in your document, were those the equations that you derived or that you obtained from somewhere else?
Are the HillTech muscle equations or the ones concerning the linear actuator, the ball nut, and the ball screw?
You had several of them in there.
Well, all the equations for concerning the musculoskeletal system was derived from the HillTech muscle model, a couple of research papers that we found online, as well as the ones concerning the linear actuator are from a Thomson Linear catalog, and as well those are universal concerning ball screws, ball nuts, linear actuators, any linear motion system.
So why didn't you identify them as such?
They're referenced in our paper, however, we'll take note of that as a reference in the presentation as well.
Just a quick question. You mentioned that your cost was $10,000 and that was less than the cost of the other prosthesis on the market, which was $50,000. Right?
Yeah.
I think there's probably a significant amount of overhead in that $50,000, right? We all know anyone who buys any piece of medical equipment knows that they mark that up by leaps and bounds, right? So do you have any comparison to an actual cost of the device that's made, just as a comparison? It's probably impossible to know that, right? But in terms of materials and things like that.
Well, the thing is, the one that MIT manufactured also uses a different kind of system since it uses electromyography, which is you're basically connected to your nervous system. So that will make it more expensive to begin with.
Yeah.
So there's no way to actually tell what the comparison is since they're not entirely the same system.
And they have custom-made Kevlar springs that we can't go buy off the shelf.
And also, in addition to answer your question, we actually did contact them and tried to find the price of manufacturing online. However, they're, as you can imagine, we did not want to release it pretty cheap.
Good luck with that one.
This ends the session. I will